Consider this scenario where someone is getting bored at home during the pandemic and is searching for games similar to their childhood favorite game, Primal Prey. Primal Prey is an indie hunting simulation game. This document is one of the test documents in the LF Amazon titles 131K dataset. Let us look at what the leading deep extreme classification algorithms predict for this test document. All the wrong predictions are typeset in light gray. As you can see, most of the predictions by Decaf, Aztec, Mac, and Attention XML are popular thriller movies, books, or action adventure games. Specifically, Decaf, which uses label text alone, retrieves the predictions primal and prey wrongly based on token similarity with the document. GalaXC is able to make 4 correct predictions in the top 5 predictions it makes. How is GalaXC able to do this? Namaste everyone, my name is Deepak Saini. To answer this question, I will describe the GalaXC algorithm and we will revisit this example in a bit. But before I go into GalaXC, let me give a quick primer on extreme classification. The aim in extreme classification is to learn to predict for a given point the most relevant subset of categories or synonymously labels from an extremely large label set. Extreme classification has opened up a new paradigm for ranking and recommendation problems by treating each item to be ranked or recommended as a separate label in a multi-label classifier. For example, we might want to formulate the problem to recommend related games to Primal Prey as an extreme classification problem where documents are Amazon products and the set of most bought 10 million products on Amazon can be treated as the label set. Another example is the Q2K application where the aim is to match a user-entered query on Bing to the most relevant subset of advertiser bid keywords. This problem again can be formulated as an extreme classification problem where the user queries become documents and the top 50 million keywords on Bing can be treated as the label set. From another perspective, extreme classification can be seen as a link prediction problem in a bipartite graph between documents and labels. This interpretation allows rich correlation structures to be inferred. For instance, suppose the documents X1 and X2 share a common label L1. If there is another label L2 which is linked to X2, it can be inferred that L2 might be relevant to document X1 as well. Such transitive inferences can be of extreme value in extreme classification settings where missing labels abound and training documents are seldom tagged exhaustively with all labels relevant to them. Current extreme classification algorithms find it difficult to model such implicit transitive relations unless the pair X1-L2 explicitly appears in the training dataset. Furthermore, existing approaches generally assume that documents and labels reside in two disjoint sets, even though in several applications, labels and documents cohabit the same space. For example, in the Q2K application, a keyword bid by an advertiser can very well be a user-entered query and vice versa. Similar is the case with product-to-product recommendation scenario. GalaXC tries to rectify these issues. At a very high level, GalaXC has two components. First, a lightweight GNN architecture that effectively utilizes multi-hop neighborhoods at extreme scales to offer multi-resolution embeddings for documents. Second, high-capacity extreme classifiers and a label-wise attention mechanism over the multi-resolution embeddings. I will now describe each of the two components in detail. Let us start with a joint document label graph. For example, for Q2K application, this graph can be obtained by taking all the queries and keywords in a specific time period. These queries and keywords are nodes in the graph and there is an edge between a query and a keyword if the keyword led to a click on the query. Further, if a query and a keyword have the exact same text, we collapse the two nodes and so finally the graph is not strictly bipartite. GalaXC's multi-hop GNN architecture allows a document to, in successive hops, aggregate information from its own labels, then related documents with which it shares labels, and finally other labels present in related documents. Okay, so this is how the graph convolutions are done. We begin with embedding A0 for each node n in the graph. These are embeddings obtained based on the document and label text. For example, for the Q2K application, we use 64-dimensional CDSSM embeddings. Now each node takes its own A0 and the A0 embeddings of its neighbors and applies the convolution block C1 to get A1. This operation is repeated for each node n using A1s and C2 to get A2 and then again using A2s and C3 to get A3. As you can see, for a given node, A1 incorporates local information based on immediate neighbors and A2 and A3 include more and more global information. A1, A2 and A3, each of these are then passed through transformation blocks T1, T2 and T3 to get V1, V2 and V3. This slide gives the details of the CK and TK blocks that I just talked about. GalaXC employs GIN style graph convolutions. So each graph convolution block CK is parameterized by a learnable scalar epsilon k. The transformation blocks are residual layers with skip connections and intervening ReLU and batch normalization layers. In extreme classification with millions of labels, label set can have significant variation in terms of semantics and statistics, and thus each label can have a different view of the graph. To this end, we propose a novel label attention scheme that allows each label to attend to the different levels of neighborhood for a document. Having got the multi-resolution embeddings V1, V2 and V3 for a document, there is a per label attention mechanism to allow each label to weigh these different resolution embeddings for a document differently. So each label has three free parameter weights alpha L1, alpha L2 and alpha L3. The embeddings of the document X specific to the label L, referred to as XL in the slide, is then obtained by taking a weighted sum of the VNs based on alpha Ls. Tail labels do not have sufficient context because of their low connectivity in the graph and might benefit from embeddings that cover a larger neighborhood. Whereas data-rich head labels might prefer focused embeddings offered by smaller hops, potentially to avoid topic drift. And this is what we observe. For instance, this plot shows the softmax normalized attention weight scaled by the average norm of the corresponding hop embedding of trained documents. As you can see, extremely tail labels give more weightage to hops 2 and 3. As we move towards more and more head deciles, the weightage of hop 1, which incorporates information just from the immediate neighborhood, increases, whereas that of more global neighborhood in hop 2 and 3 decreases. Okay, we now have the representation of a document X specific to the label L, X superscript L. Then there is a separate classifier for each label WL. The score of the document for the label is given by the dot product between XL and WL. At training time for a document, this loss is not evaluated on all labels, but for all of the positive labels for the document, but only some sampled negative labels, which is much less than the total number of labels. We initially warm up the network parameters by running a few epochs with randomly sampled negative labels, and then fine tune the classifiers with hard negatives. After the random negative phase, the parameters of CK and TK blocks are frozen. We then get what we call graph embeddings by taking the simple average of the three resolution embeddings for documents and labels. An approximate nearest neighbor search index is then built on the label graph embeddings. The hard negatives for a training document is obtained by querying the document graph embedding from this approximate nearest neighbor search index. Hence, the efficient training of GalaXC follows the deep XML framework. The key idea in deep XML framework is to decompose the extreme classification task into 4 simpler subtasks, leading to scalable and accurate training. At prediction time, approximate nearest neighbor search on the init embeddings A0 is used to introduce the novel test document in the graph. The GNN architecture is used to obtain the multi-resolution embeddings of documents and labels. As before, an average of these embeddings for documents and labels give us the graph embeddings. The graph embedding of the test document is queried from an approximate nearest neighbor search index built on the label graph embeddings. This shortlist of say 500 most likely labels is then re-ranked using the label-wise attention mechanism and label classifier to make the final predictions. Let us revisit the example of primal prey. When introduced in the graph, this test document gets connected to the training document carnivores, which in turn is connected to the nodes carnivores 2, carnivores 2 Ice Age, carnivores 2 Jewel Case, and carnivore Cityscape. GalaXC is thus able to make use of higher order graph correlations and retrieve the correct predictions. Let us now look at some results. This slide presents the results on standard cold start scenario where predictions are to be made on novel test documents. LF Amazon titles 131K and LF Amazon titles 1.3 million are product to product recommendation datasets created by mining the bot together logs from Amazon. LF Wikiseo also titles 320K dataset is created by mining the See Also section from Wikipedia pages. So for a Wikipedia page, its title is taken as a document and the Wikipedia pages mentioned in the See Also section of the page become the labels. Compared to leading deep extreme classification algorithms like MAC, Attention XML, X-Transformers, DCAF, and STEC, GalaXC can be up to 18% more accurate while being 2 to 50x faster to train and 10x faster to predict. The core utility of extreme classification comes from being able to accurately predict tail labels. These are labels that are rarely seen during training. Predicting these tail labels hold the key to good recommendations that are not currently being made by other algorithms and that might pleasantly surprise the users. GalaXC's gains are disproportionately more in propensity scored metrics, which reward predicting tail labels comparatively more, indicating that GalaXC can perform relatively better on tail labels. Specifically, compared to decaf, GalaXC can be up to 3% better in PSP at 5 metric. Further, as you can see in this graph, GalaXC's better predictions on tail labels are the major contributor to GalaXC's performance gain over baseline methods. For the warm start scenario, experiments are carried out where half of the labels are assumed to be revealed. The experimental datasets are created from the previously mentioned benchmark datasets by following three steps. First, retain only those test documents which have at least one label. Second, for these retained documents, consider half of the labels as revealed and the other half for evaluation. And third, the retained test documents and their revealed labels are made available to all algorithms at training time. As can be observed, the gains of GalaXC over baseline methods are comparatively more here compared to the standard cold start scenario. This is because GalaXC, owing to it using a joint document label graph, can exploit the revealed labels better to correctly introduce the test documents in the graph. This slide presents the results from the proprietary Q2K 450K dataset where GalaXC is compared to generative models like GPT-2, Siamese models like TwinBERT, and graphical models like pSymRank. GalaXC is also compared to leading extreme classification methods. We also present results for GalaXC AUX test, where auxiliary data sources like related searches and co-bided clicked keywords logs could be used to introduce test documents in the graph instead of a approximate nearest neighbor search. And further GalaXC AUX train, where query links were added at training time itself. Such connections obtained from supplementary sources of data can help increase the quality and quantity of primary training data alike, particularly helping data scale tail labels and documents. Owing to the joint label document graph, GalaXC is able to seamlessly incorporate such auxiliary sources of data. An efficient implementation of GalaXC in PyTorch with mixed precision training helped it to be scaled on Q2K 50 million dataset with 97 million documents and 50 million labels. GalaXC was deployed on the Bing search engine to perform A/B testing on live search engine traffic for the Q2K application, where GalaXC could improve the click yield by 1.5% and coverage by 1.1%. Further, human labeling by expert judges established that GalaXC could increase the quality of predictions by 16% over state-of-the-art techniques in production. As an example, for the query brother PE800, GalaXC could exploit its graph to learn that semantic concepts like sewing and embroidery are related to the query, which can't be inferred based on the query text itself. GalaXC could thus bring new keyword matches like brother embroidery machine and brother PE sewing machine, which were not captured previously by other techniques in production. The document and label embeddings trained collaboratively using GalaXC can be of independent interest for extremely low latency applications which disallow the use of extreme classifiers and allow only approximate nearest neighbor search calls at prediction time. Compared to embeddings offered by Fasttext, Aztec, and Decaf, GalaXC's embeddings were found to be around 15% better in recall at 100 on two benchmark datasets. The next two slides present the ablation experiments conducted to investigate GalaXC's different design choices. I'll skip these slides in the interest of time, but the details can be found in the paper. To conclude, GalaXC is an algorithm for extreme classification which tries to learn better document representation by incorporating neighborhood information with the help of a joint graph over documents and labels. It further tries to learn better classifiers using a per label attention mechanism. These contributions allow GalaXC to be up to 18% more accurate than leading deep extreme classification algorithms, with GalaXC performing particularly well for data scarce tail labels. It is further demonstrated that GalaXC can efficiently utilize partially revealed labels in warm start scenario and other auxiliary sources of data in general. GalaXC can be 2 to 50x faster to train compared to leading deep extreme classification algorithms and can be efficiently scaled to datasets with millions of labels. This helped it to be deployed in the Bing sponsored search stack with real world gains over state of the art generative extreme classification IR and two tower models. Thank you.